Hello and welcome to the lecture of Optimizing CNN Part 1. In this lecture, we try to understand why deeper network is not always good. Then we discuss the problems of deeper networks. We start with the vanishing gradient problem and how activation function is used to solve this problem. And then we try the limitation of activation function for fully solve this vanishing gradient problem. In our previous discussion, we have observed that in the deep linear network, it essentially models the input in different layer of abstraction. So, for example, here, this is a vision hierarchy for recognizing handwritten text. Now, this handwritten text is being as an input. This may be a pixel modalities. And the first hidden layer try to model the edges, while the later layers, strokes and letters. Now we can see these modeling are in increasing of their complexity from initial layer to the final layer. So that is one of the major advantage of deeper network over the shallower network. Another example what we can see that this is a typical visual example of the face recognition, that here the pixels. First hidden layer we learn the edges or model the edges, next the object parts, and in the finally we try to model the objects. So that's why we have a general sense or general idea that deeper the layer, the robust the network or stronger the network, definitely with respect to the performance. Now, what is important to understand, or the question comes, is always a deeper network is better? If we keep on adding this hidden layer between input and output, is it going to give you a very good result always? That is the basic agenda, or that is the question that we are going to discuss in this module of the course. Okay. So first, what we are going to understand from the deeper versus shallower nets. We have observed, as we said, in general deeper network give the better performance. But if it is a very deep network, that sometimes we start with this example, that it sometimes it is not going to give you a very good result. Just for example, this is in this CIFAR 10 data set. You see the error rate in this particular question or in this figure, that it is the testing error is higher for 56 layers. So definitely what we understand or what we concluded, there may be overfitting, because we have already discussed, if there is a complicated or complex or model complexity is very high, there is a chance for the overfitting. The training, the testing error, this 20 layers has less error, while 56 layer has a higher error. But if you go to the training error, still we can see that 56 layers has a higher number of error rate. Why it is so? Then this thing is not because of overfitting. Overfitting may be worse in the situation, but this kind of situation, it is not due to overfitting. Some other reason. Let us find out what are this reason, why this kind of higher or deeper network somewhat fails with comparison with the lower or shallower net. Now, first of all, understand if there is a this two net, this is a very deep network, and this is a shallower network. Now, at least one thing we should say, that if we think that this extra part, if we just avoid, these two networks should basically perform equally. So what we'll say, the deeper net can represent any mapping that shallower net can, because these are the two same layer. And if we put identity mappings, just copy the output here for these additional layers. But still we find that there is some problem with deeper net. So that problem, what we have to understand. So one problem, there is definitely some problem. It may be overfit, but even when we can see there is a training error also. In training time also there is error is increasing, that it is not only overfit, there is something else. So that is with say, but in practice it often underfits on the training data also. So the one of the major reason is called harder credit assignment problem, that we have to understand. But one very important conclusion, the deeper is not always better. So the basic agenda of this lecture is that we have to understand the problem of the deeper network, but somehow we have to know how to handle the situations. That's why this is very, very important when we are designing a convolution neural network. Okay, let's see. Now, first off, we try to understand what are the major problem. That's why deeper network is not performing well. First of all, that we understand the vanishing gradient or exploding gradient. We stick on the vanishing gradient because we already discussed it somewhat. Then another, this what we have seen, this credit assignment problem. This is basically due to internal covariance shift, that we are going to understand what is this mean and how this problem can be solved. Then definitely overfitting is there. Already we have seen some sort of regularization technique, cross validation technique to handling overfitting. We'll see here that how dropout can be used, and computation cost, definitely another disadvantage of the deeper network. So what are the solution we are going to propose in this lecture? That choosing proper activation function. To some extent we handle vanishing gradient, but we'll see it is not, this choosing proper activation was not enough, but that will be seen in the later lectures. Another important thing, the batch normalization to handle this internal covariance. Okay. Then parameter initialization being used for handling this deeper network, dropout for resisting overfitting, and some sort of weight sharing to reduce the computational complexity, and data augmentation being used for basically to resist overfitting. If we have not enough data in our supervised learning paradigm, then we use the data augmentation. So these are the major problems and these are our solution. So in this next 1-2 lectures, we'll discuss these things and how actually we can come up with a more robust and more powerful convolution neural network. Okay, to understand why the deeper network fails, first we consider the credit assignment problem. Let us first define it. What do we mean by grid assignment? Now consider a situation like this, that in this particular situation, what we have seen, that there is a neural net of different hidden layers. Now there is a one neuron that is for output, that is from input, and this is in forward direction. So let's say for in layer 4 there is a neuron. The question comes that how a layer 4 neuron know the intended output if all the previous neurons are work properly. Okay, the similar questions come in layer 2. How it know the what will be its output if all the above neurons are working properly? Because in the back propagation, it is these weights are being updated from output to input direction. So now with this example, what we understand, if we have to find out that the particular neuron or a set of neurons, that is the major problem of a particular, to making a particular neural net faulty, or that is the major reason to it performing not very well. It is very challenging to find out one or that many number of neurons. So that we have seen here, that it is defined as a challenge of determining which specific neurons or connections weights are responsible for the overall error and rewarded for the reinforcement learning case. So this thing, if we have to find out that which specific neurons or connections or weights are responsible for the problem, this is called credit assignment problem. And how to find it, definitely it's a challenge, very challenging task. And it becomes more and more difficult if the network is deeper, because feedback is delayed or distributed across many layers. In deeper network, there is a lot of layers, and it making it hard to know which internal step to adjust for better performance. And this is basically called the credit assignment, to find out that the faulty neuron, or for which neuron or neurons are basically responsible for this, the problem of the total neural network, and it's becoming, the result is not coming properly. Okay, now you can understand what we mean by this. Now our next problem that we already discussed few things about, what is the vanishing gradient. Now vanishing gradient is a problem that you have to understand it in deep. So you have to understand what is this activation function is doing. If we see this activation function, if we recall it, that this is sigmoidal activation, and if we take a derivative of this sigmoid function, we get this. Now this is less than 1 value and this is yj. So if it is so, then definitely this thing is less than 1. So for this sigmoid and tan h, this is just a secret version of sigmoid. The derivatives are almost less than 1. Now if we recall it, that what happens in case of backpropagation, then what we have seen, that in chain rule, these derivatives are basically keep on, can say, multiplied, or getting the error gradients in the initial layers, basically backpropagating from final layer to initial layer. And when we are going from final to initial, So then these derivatives are keep on. If we multiply many times with number of less than 1, definitely what happened? The gradient sinks exponentially. And that is because that the major reason, that is because this gradient is vanishing, called vanishing gradient problem. So you see here, when in the layer from final layer to initial layer, gradient is exponentially decaying. That these things we want to see in bit visually, try to understand how actually it is happening. Now let's see. Now take all this. The slide you already studied before. Just for your recapitulation. Now here in the output layer, this is your error gradient. D is your this predicted output. This small d is your target output. Take this difference, take square and normalize it. This is your error. And if with respect to this wg, this thing, this d of e0, this is the error gradient with respect to the output weights. Now if we this from this output weight, due to the backpropagation, we are propagating from final to initial layers. So due to this to this to this and this to this. And using chain rule, every time we are find that this error, this particular error with respect to this particular hidden layer. So in a kth hidden layer, this error is this. In k minus 1, the k minus 1 hidden layer, this error gradient is like this, and it is being done chain rule that we can know very well. Okay. Accordingly, we are updating the weight. When it is going to the initial layer, you can say this number of multiplication become high and high. And if this particular k is very high, that means the hidden layer, number of hidden layer is very big, and depth is higher. Definitely this multiplication become lot of multiplications. And when we are multiplying with a number less than 1, that we'll see later. And when we this error gradient at different layers, and this error gradient used for this weight updation step. So as a whole, this is the back propagation. Now we'll see here is how the gradient is becoming low and low when going to the final to initial layers. Just to see that what we have to find out this. So this from by this we can find this. For the hidden layer 1, that we have to find out. Now we cannot get the direct, so we have to depend on the H2. So definitely this is in chain rule, we use the chain rule here. Then with the H2 depend on H3, this kind of chain rule. That's what we have seen, and definitely this. So basically what we have to understand here, in this way we are back propagating this particular error gradient is back propagating using chain rule. And what is happening ultimately when we get this, there is a lot of multiplications here with these values. Okay. So the question is, what happens if these values are small? Because what we have seen in case of our activation function of sigmoid and tanh, this is less than 1, these activations. And now you can see here this activation is keep on multiplied. And if you know about simple arithmetic, that if we keep on multiplying with value less than 1, then it will be becoming very less and close to 0. So when these are small, the gradient signal gets smaller and smaller as it back propagates further, and eventually is very close to 0. So this eventually vanishes. This is called vanishing gradient problem. So in backpropagation process, gradient signal close to the output layer is strong, that we have seen here, but it becoming smaller when it reaching close to the input, that we have discussed. It is from output, and deeper the model, the smaller the error gradient to the initial layers, because the successive multiplication is then was managed. So due to decaying of this error gradient, initial layers input weight updation becoming insignificant, because definitely we can understand from here that in this rule that this is basically using for weight updation, and this become very close to 0. So it is not updating at all. Updation is almost, this t plus 1 is become almost t. So there is no almost updation. So that's why this is important to understand that this, due to this decaying initial layers, the weight updation becomes insignificant. This makes the convergence very slow, almost stop. And this is the basic, this is called the vanishing gradient problem. Question comes, how to solve it? That we'll see that how these problems are solved. Now, to solve this vanishing gradient problem, to find out what are the activation function we generally used for our convolution neural network. First of all, we start with sigmoid, then we will see tanh, ReLU and leaky-ReLU functions. So first we start with sigmoidal nonlinearity. Now as we have discussed before, this is the sigmoidal nonlinearity, 1 by 1 plus e to the power minus z. And this is the function that it's looking like this. We already discussed so many times. Now also we have seen that if we take the derivative, it becomes sz minus to 1 minus sz. So one important, if we plot this function, with that the maximum derivative value is 0.25 and it is very close 0. This derivative is becoming very close to the 0 when it becomes near what we go here. So now in this situation, what happened? Let's try to understand for our backpropagation thing. When we backpropagate, we calculate this. This is error gradient that is backpropagated here, and from where we get this, the previous layer, that it is del of L, del of S into del of S of del of Z. So what is happening here? This, if a neuron is saturated neurons, that means what? Neurons that output very close to 0 or very close to 1, that kill the gradient during backpropagation. How? In the backpropagation, what is basically doing in this, just it is d of dl is del of d of s is multiplying of del of s of del of z. So this is multiplied with, and this is a smaller, and if it is smaller, then it decaying the signal to the next layer. So this is the major problem with this sigmoidal activation function or sigmoidal nonlinearity. So the gradient, if we keep on doing this multiplication and layer, there is a lot of layers, so deeper network, then this gradient are going to slowly vanish until they die off or they reach the initial layer. Once it's done, gradient flow stops and the neural network stops. That is the major thing with the sigmoidal activation function. Now, if we just summarize, what is the problem? Is saturated neurons, the neurons that output very close to 0, 1, 1, essentially kill the gradient during the backpropagation, which caused this vanishing gradient problem for sigmoidal nonlinearity. This output is not zero-centered, that is one small problem, and this e to the power is exponential function, that is exponential computational complexity. So what is our next alternative? Next alternative is tanh. Not much thing is different. It's basically a kind of scaled version of the sigmoid. Okay. Just it is initially it is here, now it is 0 center. So it's 0 center and somewhat better than sigmoid. But it is not essentially too much improvement, because this is the derivation effect plot derivation still crosses the number to range -1. Okay. So what happened is still the kill the gradients. Still it kill the gradients and causes the vanishing gradient. It's somewhat better for its 0 center, but the major problem is not solved for 10H function. Okay. Now, what we generally do for this, replace this with rectified linear hybrid, that is called Rayleigh activation function. Now, this is very interesting function. First of all, it's computationally very efficient. You can see this is a very straightforward function. And if it will derive it is del of dz 0 if z is equal to less than, and if it is 1 it's greater than 0. So this is. So one major thing, when it is greater than 0, it doesn't saturate in positive region. So positive region, when it is greater than 0, it is not saturated. Okay. And it converts faster than sigmoid at that age. But there is a problem here when it is less than 0. If neurons were updated in a way that the input to the Rayleigh function is always negative, so this portion, the output becomes 0 and the gradient becomes 0. That neuron effectively dies and stops contributing to the learning process. This is called dying Rayleigh problem. Okay. So this effectively similar this vanishing gradient. So this portion it is somewhat better, and but this portion is a problem. But still we can say it is better than sigmoid or 10H. To mitigate this dying Rayleigh problem, another very interesting innovation is done. It's called leaky Rayleigh or leaky rectified linear unit. So what it will do? It will do that this point 1 is a that this here. It is not 0 but something. Okay. So this alpha is a very arbitrary value. 0.1 is just we choose this arbitrarily. Alpha is any value and it's very small value. Okay. Now it essentially solves this Rayleigh, this dying neuron problem. Avoid 0 gradient by introducing a small slope. So this is like this. Okay. And it doesn't saturate, computationally efficient, and converts faster than sigmoid 10H practice. So there is a lot of improvement is being done over that. It theoretically solves this problem, this dying Rayleigh problem. But question comes, if this is enough to handle the vanishing gradient for the deeper network completely? This is very important question. Now here we just give this slide bit forward because this is very important to understand. Now it cannot complete solve the vanishing gradient. Why? It is typically less than, this alpha is very less than 1. This alpha is less than or negative inputs. And during backpropagation, multiplying with the small gradient across many layers still cause the gradient to decay exponentially. So it is not solved. This is the major reason is this, the small negative gradients. The Rayleigh provides a non-zero gradient found with this range multiplying by a small slope. It may be 0.1, 0.001 something. And still much less than 1. And deep networks, this small value still cause the product of gradients to approach. So in this negative side, this vanishing gradient is still there. Actually, this leaky Rayleigh is designed primarily to fix the dying Rayleigh problem. of ReLU. So that is not a complete solution of vanishing gradient. And definitely this leaky ReLU avoids the hard zero derivative of ReLU. So basically this is this cumulative effect multiplying many gradients then one still leads to the vanishing. So these things are major problem of ReLU. So it is definitely better than sigmoidal or Stanage, even ReLU, but it is not enough to handle, particularly for the very big or very deep network. To solve the vanishing gradient problem in deep network, technique like residual connection, what we'll see in this later slide, it's called ResNet. The CNN with residual connection. That is very interesting, very you can say nice innovation, a sound innovation you can say, that this gradient bypass layers entirely. Okay. So to summary, in this lecture, we try to understand why deeper network is not always good, what are the problem and the solution of the deeper network. Then we understand vanishing gradient problem in depth. Then we try to understand activation function, how activation function is being used to solve this problem. And then we understood that even the activation function do some well, but this is not enough to solve the activation, solve this vanishing gradient problem. So we continue this lecture optimizing how optimizing next part also. Thank you very much.